Some of the stuff that you're going to be looking at is about motors. Everything is about motors. Nobody's going to hire you to put a fraction of a horsepower motor in a building. Most of the stuff that we do, guys, are 7.5 horsepower, 3-phase or higher in a lot of commercial buildings. So you're talking about bigger motors. With bigger motors, every motor that when we talked about motors, guys, there's certain things that motors have to have. One thing is a disconnect. Everybody knows what a disconnect is for. We've been talking about disconnect, and we sized them last quarter, and we will continue sizing them next quarter. Disconnect is safety factor. It's not meant to be a controller, turn on and off. It's meant to push the button, stop the machine stops now, go turn it off, lock it, tag it, and go work on the equipment. You or any mechanical guy who need to work on this equipment. If you guys remember when we talked about disconnect, when you have motors, guys, when I used to teach motors, I told you guys a lot of students used to think motor is just that little motor here. This is nothing. That's not why we have motors. We have motors because of the machine that's driven by motors. That's why we have a career, because people need us to drive their machines, and they can drive their machines either by mechanical motors, right? Then they don't need us, or electrical motors, and they need us. So you can drive most of the equipment. The industry experts have standardized in driving equipment by electrical motors because it's affordable, clean, and so it's affordable, clean. You can control it. There's a lot of advantage of driving an electrical motors versus driving a mechanical motors, as in burning gas here and making this motor run. You can have a motor that drives by gas. Okay, so this is why people like us. That's why we have a career, as a matter of fact, because of these motors. So when we have a motor, I want you always, please, every time you think of a motor, think of the machine that's going to be driven by this motor. This machine could be right next to the motor, coupled to it, or it could be, or it could be 10, 20, 30, 40 feet away from this motor, built it together with a V-belt or with the gear or whatever. Okay, so that's the most important thing about this picture, is understanding that motors always drive machines. Then, for safety factors, we talked about, guys, that this disconnect that you're looking at have to be within sight. It has to be within sight of the motor, the machine, as well as the controller. Now, all these could be, a lot of the time, guys, these are all in one, right? If you have an air handling unit, if you guys have an air handling unit, you're going to find the air handling unit machine that you're driving, as well as the motor, as well as the controller, all in one big box. Great, but it doesn't have to be. It could be one in big box, or it could be in different boxes. If they're different boxes, then the disconnect have to be within sight of the three of them, or you have to have one disconnect for each one of them, believe it or not. Now, most of the time, people are smart enough to have a disconnect. Most of the time, guys, they will be right in one big enclosure, and we have one disconnect to disconnect all of them safely. Any question, guys, about that? Within sight means, as we define it by the code, within sight it has to be 50 feet or within sight. 50 feet, no barrier, so you don't have to jump 10 feet to reach the disconnect. Same level, 50 feet, no barrier in between. Any question, guys, about that particular one, the disconnect? So disconnect have to be within sight of the controller, the motor, and the driven machine, or you have to have one for each one of them. I'll show you a couple of nice pictures. That's what I want you to take. Can I dare to write one thing, guys? Most of the time in a commercial building, I would dare to say 90% of the time, you are going to be one disconnect and all the controller, the motor, and the driven machine all in one big box. In a commercial building. Now you go industrial, it's completely different. You can have the motor laid all over and the machines all over and the controller all over too. So it changes when you go to industrial. For commercial building, that's typically what you're going to have most of the time, all of them right next to each other and disconnect right next to them. Done deal. Any question, guys, about this? Now we talked about sizing the disconnect. When you size this disconnect, two things. First, the horsepower rating, and second, the amp. It has to have amp. Amp is easy, 1.15 from the code, and we did a lot of calculation on that one, guys. You take the full load current of the motor, multiply by 1.15, size it, and I showed you guys in the code in DeWalt where you can find the standard sizes, 30, 60, 100, 200, and so forth. Done. And horsepower rating. Horsepower rating, if this happened to be 100 horsepower, then I need a disconnect that can able to interrupt a 100 horsepower motor. So disconnects that drive motors, guys, are rated in horsepower and amps. Anybody knows why horsepower and amps? Because interrupting an energy that's going to a rotating machine is more dangerous than interrupting an energy that's going to a light or energy that's going to a heater. There's electromagnetic kickback. So this one has to be rated for horsepower, meaning it will be able to interrupt the power that's at that amount of power. It's not supposed to though, but if somebody come accidentally or intentionally when this machine is running, you're not supposed to open this when it's running. If somebody, for whatever reason, decides to open it while the machine is running, this is not going to blow off the wall. That's what the horsepower rating is. Otherwise, if it's not horsepower rating, if somebody, and this is, somebody could come here and turn it. I have no idea what a disconnect is, think it's a controller. The whole thing is going to blow off the wall if it's not horsepower rating. Does that make sense? The gravity of a horsepower rating? Horsepower is power, obviously. Okay, so that's one thing I want to show guys. Again, you have to have like we said, the controller have to be within sight of all of them, or you have to have one for each. Only so the rule. This is the 90% of the time. This is really one machine, and 90% of the time, a disconnect right next to them, within sight of them, within 50 feet. 90% of the time. And this is how you should design the disconnect right to the machine. Now, what happened under special conditions, guys? If the location only under special conditions, if you couldn't achieve that, then these will have their own disconnect and the controller. So this goes with this, and the controller is going to have its own disconnect because they were in different locations. You completely want to avoid this. Why? Price? Are you kidding me? You're going to have two disconnects, horsepower rated. So you're going to avoid. This is bad design. Unless you have to. You really want to avoid that. So this is an exception. They use it a lot in industrialized and commercial building. This is an exception, guys. And again, I can't emphasize, it is an exception where you can have your disconnect located anywhere else in the building, and you have your controller and motor and machine located anywhere else from each other or anywhere else from the disconnect. But you have to be careful. Then your disconnect has to be able to be locked in the open position, like you can see. All of them are. They can be locked, as you can see on the wall here. And here's to apply the exception. The disconnect is, I can't emphasize, here's what the word is. It's impractical to put the disconnect next to the equipment. How do you define impractical? It's dangerous. You don't have room. So impractical to put it. So the rule is you have to have the disconnect next to the equipment and the controller, the 90% of the time. Or might cause additional damage or increase hazard to the personal property. You put a disconnect right to a machine, guys, that mixing chemical equipment. If somebody accidentally disconnected and it stopped this machine, you're going to have an explosion. You're going to have a big mess on you. You can imagine how you really need to disconnect, isolated in one location where nobody, maintenance people, accidentally disconnected. That becomes a big deal. And also the individual installation, they're smart people, look at that. There's individual installation where there's written safety procedures in the workplace, where the condition of maintenance and supervision only qualified people like my friend here, supervising and servicing the equipment. So these are where your equipment are locked under behind doors, and if you have to do maintenance on that one, you only call electricians, qualified electricians to maintain your equipment. Under these circumstances, you can put your disconnect anywhere else. This is a lot, guys, in wastewater treatment plant, manufacturing. You have their own electricians. U of M, they have their own electrician. 3M, they apply to them. They have their own maintenance electrician. They have written procedures how to disconnect things. So you can't apply this to a commercial building, where you don't have on-staff electrician to maintain the system. You have to call, or the janitor guys can have access to all these disconnects. You can't apply it. Any question about the exception? So the rule, remember the rule. The rule is the disconnect right next to the equipment. Only exception that you put the disconnect far away. Okay, so these are what I wanted to emphasize. If you have a bathroom fan, now we're talking about baby boys, like you guys have bathroom fans. If you have a bathroom fan, your disconnect can't be the snap switch that control the bathroom. If you guys have a fraction horsepower, 1 horsepower or less, these are, they allow you to use a snap switch like in the bathroom. Turn it on, off, and at the same time act as a disconnect.
It says in the book that thing has to be horsepower rated. How can you tell by looking at one?
You can't. You really can't.
Okay.
Yeah. You know, what do you mean
Well,
the snap switch?
Yeah.
The snap switch. They have. I'll show you one in our. Some of these guys, if this is a controller, but this is actually for bigger motors than fraction, not for bigger than fraction. For like 2, because up to 2 horsepower, you can have a snap switch like this. With inside it is an overload. If you go to our lab here, Dunwoody, I'll show you. We will take you there. It looks exactly like one of these guys. You cannot tell by looking at it, but if you open it, you'll find a place where they have an overload in it, overload protection.
so standard little one that you buy at.
It will work for a fraction horsepower. Fraction as in a quarter, a third, like the bathroom fan in your house. Yeah. Yeah, yes.
I mean, typically in a furnace, most of it.
Oh, yeah.
Furnace.
Residential furnaces I've ever seen are pretty healthy sized motors, but they always seem to have snaps.
Snap switches, absolutely.
And
fraction of a
you
horsepower.
just grab the switch off the shelf at Home Depot.
Absolutely.
It's good.
As a disconnect, absolutely.
So
Absolutely.
It doesn't care if it's horsepower rated.
Not at this size. Not at this size.
Naturally,
Yeah.
an industrial more robust switch would probably.
You know what? Naturally, a more 3-phase. I wouldn't put these with a 3-phase equipment. These are guys, we're talking about single-phase equipment. I have a 3-phase piece of equipment. Most likely, it's going to be in 2, 3, 4, or higher, even 5 horsepower or higher to make it available. Then you're going to have that one on the wall. So, okay, so these are just the fraction of horsepower where you can we can use snap switches. This is a list, guys, of overload sizing. I don't go over this with the designers. It gives you 3 units. Just like what if you have a full load motor. Look at this. This is your full load motor. This is for 3-phase. This is for single phase. So if I want to put a controller thermal unit heater, if I have a motor, let's just go pick one little one randomly here. Take this. If I have if this is thermal unit number B2.40 can get me a full load amp of 1.45 all the way to 1.63. And you can, that's the range of the full load amp that these can cover. When you size the heaters, you size them, it'll give you, to go buy a motor that can cover it between these amps, you go buy B2.40, will cover you between these 2 amps, ranges of amps. I don't like to go over that one with at least with the designers. This is more important, guys. This is my favorite. A motor like this one calls inside it. You have your disconnect, the fuse, overconduction device, controller, overload. Typical, right? This motor is running at 10 amps, 10 amps, 10 amps. Everything is sized perfectly. This is 12.5 amps, sized perfectly based on the code, right? And this is the 17.5 fuse. And this will move me with a 20 amp, right? 17.5, we don't make 17.5, so what do you think it's going to do? 2.5, this one, so this is a 10 amp horsepower motor, typical design for it. Cool? Typical design. So
is the fuse in lieu of a circuit breaker, or is it
in lieu of a circuit breaker? Absolutely. Fuse or circuit breaker. A lot of people like fuses, guys, with motors because, you know, fast acting, they give you better protection, and so forth.
Then for sizing the overload, we do 155.
Thank you. In this case, when we size overload, there are 2 multipliers, 1.15 and 1.25. 1.15 for all the motors. 1.25 for only the motors that have a service factor of more than 1, or for the temperature rise is 40 or less. 40 or less. Then we can multiply by 2. So in this case, this has a service factor of 1.5 service factor. What does that mean? I can overload this motor 1.15, I'm sorry, 1.15. I can overload that baby 15% extra and still okay. Not going to burn it. Can you guys look at this, how this motor works? We took the rotor out. These are just the coils, right? So let's see what happened. These are one of the nicest pictures that we have, guys. Let's see what happened now. This is normally under normal condition. You can run this baby forever, forever. You can make it run forever. Look at that. I have 10 amps. Most likely these conductors are number at 12 and a half. That will give me, I can go for number 14, right? As low as number 14, no problem. I can put number 14, number 20 amps. Can I? Yes. Why? Because it's a motor. So I can use number 14, but most likely if it's a commercial building, I hate to say it, I don't like to go person less than number 12, but you can put number 14 on that one. It's okay, right? 14 is good for 15 amps. Everything is cool. Now let's look what happened if you overload that baby. If you overload that, and look what happened if you overload that motor. Now you overload it. So what does overload means? You went, when they overloaded, did you guys see what happened to the motor for the top? What happened to the windings? Can you see what happened to the windings? The two pictures? What happened to the windings? You fried the windings. You did fry the windings. So you overload, the motor is rated for 10 amps and you're pulling 15 amps. How would you pull a 15 amps out of a 10 amps motor? Add more load on the machine. The bearing on the machine are rusted and they're not working good, dragging the motor. So any reason the belt is not sized properly or is old and frayed and so forth, because of the overload on the rotor, look what happened. I have 15, 15, 15. Do you think a 17.5, I have 15 amp going through my motor, but my overload is sized at 17.5. 17.5. Do you think it's going to trip? The overload is going to trip and overload? No, it's not going to trip. Look at the current that I'm taking is 15 amps. The overload is sized for 17 and a half, and this one is sized for 20 amp. Do you think the 20 amp is going to trip first? That's full load. No. Do you think the 17 and a half? This is as high as you can get, 17 and a half, and I'm still at 10. Do you think this is going to trip? No. So this motor is going to be pulling 15 amps continuously until it burns itself. Until it burns itself. If you size it at 17, if you put the overload protection at 17 and a half. But remember, the overload protection was supposed to have been sized at what? 12 and a half. If you size it based on the code at 12 and a half, as it should have, right? If you size it at 12 and a half, 12 and a half, 12 and a half, instead of 17 and a half, and you're pulling 15, what's going to happen to the overload? It's going to open, and it's going to save you $300-400 buying a new motor. Any question, guys? So if you look at these pictures, the inside of it is completely burned because of overload. That's why we have the overload. And that's why they don't want you to go higher than 12.5%. This should have been 12.5% based on 1.25 times 10, right? Right? It should have, based on the code, you take the 10, multiply by 1.25, and that will get you 12.5, and then you set these overload at 12.5. But they sent Nick there, and he said, well, I don't care. I'm gonna go jack that baby up to 17 and a half. It has to be a mistake that you have done for this to happen.
What should the fuses have?
The fuses should have, yeah, fuse is 20. That is.
I thought it said
No, the same example that we did. It was 20 before. The same picture.
the current times 1.15. I take 10 and multiply it by 1.15.
That's for the conductor. For the fuse, you guys remember how we size the fuse? We size the fuse, if it's dual element time delay fuse, we size it based on 1.75 times 10, and that will give me 17.5 amp. Here's my fuse, 17.5 amp, but they don't make them though, so that could allow you to go to the next standard. Any question, guys, about this? This will hopefully bring home the overload for you. I do this a lot with electricians because they set the overload, guys. Okay, so the other problem that you guys have to be aware of is single phasing. Look at this situation. Now we talk about the single phasing. If we have a single phasing situation, this is a 3-phase motor, and I lost phase A because a storm took down the phase A on the transmission line or something happened. I lost phase A. What happened if you lose phase A on a 3-phase motor, guys? The motor will suck this, the current here will be 0. There is no voltage on that line. then this one, instead of being 10, 10, 10, to compensate for it, it ups itself to 17, 17, 17, right? On each, because it has to compensate for the loss of the 10 amps from the other line. Okay, 17.3. Now, if this overload is sized properly, 12.5, do you think it's going to take care of this problem and help you? Yeah, it will open. So overload will protect you from single phasing too, not just from overloading the motor. Your single phase, this is called single phasing, when you have a motor open. By the way, 17.3, do you think the fuse will protect you here? The fuse would never open. The fuse, remember, the fuse, we size them at 20 amp, yeah. 20 amp, 20 amp. And I'm pulling 17.5. Would it even wake up? No. So the only one is going to wake up and protect you in this situation is a properly sized overload protection. So you can protect from overload and you can protect from single phasing. What's single phasing? When you lose a phase or two on a three-phase system. Had this been a single phase system, who cares? The motor will stop, never start. Any question guys about that concept of single phasing? Look at, I don't know if you guys can see, look at these single phasing, look at if you don't properly protect it, if you don't protect it properly, like I decided to make, this happened, this is 12.5, I decided, Chad Kearney, because I'm a big-headed guy, I'm going to put 18 here, 18 here, and 18 here, right? I didn't size it properly. I have 18, 18, 18. Do you think the 18 is going to wake up when 17.3 is going through it? No, not fast enough to see that burn that's happening to the coil. So you lost not all the coils. It doesn't matter if you lose part of your coils inside your stator, you're dead. Your motor have to be rewind. So you have just lost $200, $300, $400 depending on the size of the motor. Because of what? Because of a tiny little overload that you neglect to size properly. Short circuit. Thank you. This is overload and single phasing. Now, when would the fuse wake up? Very good point. Well, why do I have a fuse? Here's when you have a fuse. Suppose that this phase here shorted to the ground, right? Could happen. Take this phase, shorted to the ground. This is still on and shorted to the ground. In a case like this, you're going to have a huge amount of current. Huge. You're not going to have 17.5. You're going to have close to 1,000, 2,000 short circuit. Then the fuse says, till the overload stop, don't handle that. That's my territory. I'll protect you. So the fuses, guys, are protection from short circuit and ground faults only, for the most part.
If you have a three-phase breaker, if one goes to ground, it pulls all three off.
Yes, thank you. If one goes to ground, it will pull the three of them off. Absolutely.
Yeah, I assume it's superior to three independent fuses.
Yes, because if you have a ground fault on a fuse, it will take one fuse. You're absolutely right. If I have a ground fault on a fuse, that fuse will burn, done, but these are still up and running, so I single phase. Again, single phasing. But guess what's going to protect you from single phasing though? The overload. Any question guys about overload? I like these pictures because hopefully they bring it home. Single phasing is create an overload system for you. Okay, so and you see why these windings are burned, these two, and the ones that we highlight there, because they're taking 17.3, 17.3. This winding have 0, and that's why this part here is not burned. But who cares? You lost your motor. If half of the windings or even 1/3 of the windings are burned, you're dead. A motor is either, I call it zero tolerance burn for the coils of the motor. You lost the coil, you lost everything almost. Any question guys about this? I like this picture because hopefully we did a lot of sizing on that, so I'm not worried about the sizing, and we will do more as we go, but hopefully we'll bring it home. This is a delta. Now what happened? The first one was a Y. This one is a delta, guys, and we lost a phase. And Chris, thank you, Chris, we lost a fuse. We short circuited, we lost a fuse. Or we lost a phase at the utility side, or we lost a fuse in-house because of a ground fault, one fuse. So look what happened. This turned 0, right? It's a 0 because as it should, there's no current. Now this is going to be compensated by the others, and then instead of 10, each one of them will carry 1.73 extra. 1.73 extra. That's coming from a three-phase multiplier. So if this is properly sized, it will trip, and you wouldn't see this situation. if we send Oladipo, big-headed Oladipo, he decided to put, I'm going to say just 19 here, 19 here, and 19 here, each one of them, oversize them. This will burn, and you're going to see the situation that you're looking at. You're going to see the situation that you're looking at. So look at that, this coil, this, because in a delta, look how they spread, guys. In a delta, one coil is going to be burning, because each one of these is rated for 5.5. One coil is going to be burned. But who cares? You burn your motor. So this is an example of single phasing a delta motor. Not commonly used. A lot of places, guys, we use Y motors. But if you have a delta motor, also you're doomed if you single phase and you solve the overload properly. Now look what happened. Now if you have a single phase, guys, on the primary, this is your utility transformer, press. This is utility, and on the transmission line 13.8, this is 13.8, Jeff, this is in a 13.8 system K, I lost one line, right? Fuse on the transmission from the utility. Now your building have a delta Y feed, not coming. Then look at the same thing is going to happen, guys. You're going to have, the currents are going to be different, but you're going to have, because you lost, the delta compensate for the third phase. If you have a delta, the delta coils will compensate for the last phase on the primary of the transformer, and it will give you some current. In this case, you continue the phase that you lost on the primary, continue on the secondary to pull 11.5, but to compensate for the loss, one phase will be pulling 23 extra. Who cares? Then if you overload, if you don't have an overload protection here, what's going to happen to this coil? Right here. What's going to happen to this coil that's rated for 10 amps, and now it's carrying 23 amps? It's going to burn. It's going to burn. But if you have, if you put an overload 12.5 here, and you're pulling 23, what's going to happen to the overload? It's going to open. So anyway, all these guys hopefully will help you understand why an overload is very important for motors. In a Y or in a delta on the primary transformer or secondary transformer. Okay, a couple of things, guys, that happen. And I know you don't, if you're a project manager and an engineering firm or electrical contractor, this big deal, because they hire you and they say, equipment are acting weird in our building. How can we solve the problem? And you know what, they're burning up, but we look like there's voltages here. Well, if you lose a voltage, guys, in one phase right here, we lost the voltage. We open fuse, the fuse open, and on the main, this is the main panel, and I have a fuse on each one of these. I have a short circuit right somewhere here, and I lost the fuse. This fuse is lost, the first one, open. Now I have single phase in. If you have a major motors, guys, big motors, let's say 100 horsepower motor, and I have here 10 horsepower motor. If you lose the fuse while the motor is running, but it's lightly loaded, the motor is rated for 100 horsepower, but I'm loading it only, the machine that's running out of it is worth, say, 50, right? So the motor is rated for 100, the machine is rated for 50 horsepower. So it's half loaded. I can't have a half loaded motor, just half loaded. And a situation like this, and it's running, guys, this will continue to run. At one time will heat. And oh, by the way, it acts as a generator and bring a third phase to the smaller motor, and smaller motor continue to run too. But at a higher amp though, at a higher amp. And if you don't have overload protection, they will burn. If you don't have overload protection, they will burn. So that's where these bigger generators, if you get into a building where we have 100, remember, see how the difference between 100, the 100 guy, when it's running half loaded, it will generate voltage, enough induced voltage into the last phase for this baby even to start, not just to keep running. This, if there was stop, to start even, or continue to run. If that stops, the big boy, you can't start it when you lose a phase. But if it was running, it could, on lightly loaded, say 50% or less, 30% of it is loaded, it continued to run. Any comments, guys? Any questions? The reason why we focus a lot on motors, because every machine that we put in our equipment has some type of motor in it. So single phasing can, in the book, they say can create a lot of issues. When we have any motor, guys, you have the starting current for 10 seconds. Where's the time? Almost for 10 seconds here. 10 seconds, not infinity. You can have a current of almost all motors, continuous amp 25. So this, in this case, this motor is rated for 5 amps. This is 5 amps. And when you start that baby, it's sucking out of the system 5 times 5, 25 amps. Only for 10 seconds. This is what they call it, the starting current of a motor, guys. The starting current of a motor. And that's why we size the fuses higher, the circuit breaker higher, so we can handle the starting point. Later on, and please remember that one because we're going to do short circuit coordination. When we move into next quarter, you and your friend Chad are going to be doing overcurrent friction coordination, where you're going to put the I, the current here, and the time is here. And Chad is going to be, you guys are going to be drawing a curve that looks like this. And let's just use the same example here that they're using here. Here's 5 amps. That's my 5 amps. This is my 25 amps. The same example here that they're using, except different parameters. And then you're going to have a fuse that sits right here to protect it. This is my fuse, and on this side I have an overload. Look what they do, they work together. They have an overload protection. So this one is my fuse. This one is my overload. And the red one here is motor start curve. Motor start and run curve, the motor curve they call it. So this is how they protect them, guys. When the motor starts, look at how the fuse is pushed all the way back. It allows the motor to start up to 25. But if the motor stall and keep pushing to 25, at one point the fuse is going to wake up because it's going to think a short circuit. If it doesn't start, it's jammed. It will give it 10 seconds, up to 10 seconds. Can you guys see here? It says 10 seconds. So Nick, you are a motor, you have 10 seconds to come up to speed and suck 5 times more current, only 10 seconds. If you continue to do that, continue means the time going up. What's going to happen to this when it goes up? The fuse is going to be hit. When you hit the fuse, it will open. I want you to remember this one, guys. We're going to be doing it because they call it overcurrent protection coordination. And we're going to be doing it with a software. This is bring it home, where the fuse is protecting from short circuit, the overload protecting you. Can you see how the overload is right next to the 5 amps? So if it exceeds more than 5 amps slightly, it trips. So just remember that. And the starting current, I like to do that. This area here is this area, the area that the current is going to be starting. You're giving me certain amount of amps for certain amount of time to start the motor. You exceed this one, you're doomed if you don't have a fuse. Any question, guys, about this? Any comments, any questions about the starting? Almost always the start current is 10 times, well, 6 to 10 times. We have tables in the code that we calculated the start current based on that one, guys. Control, a couple of equipment. Here's this is just a picture of an appliances that we have. So we talked about motors. Guys. Now, if you have appliances too, so motors, we know disconnect, overload, conductors, and so forth. If you have an appliance that doesn't have a motor or has a motor, or appliances also have to have some type of a disconnect. You have to have your disconnect from this in the code. You have to have the overload protection size, and you have to have the conductor size, and you have to have the conduit, of course, from any sequence book. The conduit. The conductor size is 1.25. If it's an appliance that doesn't have a motor, if it's an appliance that doesn't have the motor, they take 1.5, I believe, times the I, full load current, if it's more than 13 amps. The disconnect, which I would, and the conductor 1.25, side disconnect exactly like motor 1.15 times I, full load current. That's for an appliance that doesn't have a motor, a heater that doesn't have a motor, and so forth. All appliances, all motors, all machines must have a disconnect overcome protection device and controller. If you have the difference between appliances, guys, and motors, appliances are manufactured in standardized shapes. A fridge is a good example, refrigerator, microwaves, all these equipment, or even at a higher level, what do we call them? Dishwasher, washing machines. These are the appliances that you have. When we size the conductor 1.25, the controller on the appliances almost always is part of the appliance, the controller. We don't specify. It's almost always part of the appliances. As a matter of fact, some appliances also have the disconnect right on them. They have the disconnect right on them. So I don't like to talk too much about appliances because for the most part, we don't have a whole lot of appliances in a commercial building. We have machines that are driven by motors, and we know how to handle that one. Okay, couple of controllers, couple of coils. I emphasize, this one is the heater. They call it the heater, guys, here. The overcome protection device heater. These are the ones that overload protection. They look overload protection, non-electronic type. We don't get involved being designers. You probably didn't get involved in placing these. Look at this baby burned to ground because of a short circuit ground fault. Couple of burning fuses to protect you. And moving fast on these. These are the machines the equipment, guys. This is the equipment. If you are to design something for the cafeteria down when you go to the cafeteria, you have a lot of appliances there, 3-phase and single-phase appliances. These are where you have to have a disconnect. But most of the appliances, or a lot of appliances, they're plugged-in appliances, guys, and the disconnect itself, Chris, act as your disconnect. The plug itself act as your disconnect means. So if you go down to our cafeteria Dunwoody, you're going to find a lot of these fryers and blah, 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 all this stuff. They're all plugged in single phase or 3-phase. And if you are to work on these machines and the control system is right on the appliance, right? The control system is right on the appliances. And if you want to control them from there, if you want to work on them, unplug them, take them, work on them. Unlike an air handling unit where you don't unplug an air handling unit or rooftop units or chiller or boiler, electrical boiler. So a lot of these guys, okay, so the rest of them, guys, they're taking examples of the book, the loads that we have in the book. I know for a fact that we took, this is sizing, basically what they're doing is they're sizing branch circuits. And we told you guys before, when you size a branch circuit, continuous load 1.25 times the load, we size the overcome protection device as well as the conductor. And these are the examples that we do. Nick, my friend, remember you asked me about how do you size the overload? Here's your overload multiplier. You're going to use all other motors, 15%. This is from the code. And if the temperature rise is 40 or less, 25. If the service factor 115, service factor not less than 115 or larger, 125. Almost the default is 115. The exception is 125. Any comments, guys, about sizing overload? I know we did size overload last quarter, and we will continue to size next quarter. You guys will come and visit these again to size overload. Motors, guys, have insulation level. Remember that, Chris, the windings that got burned? That showed you the windings. These have insulation level. The insulation level, they go from A all the way to D. If you have a level of D, this means, look at this. Anybody can handle this 180 degrees Celsius? You can get 180 degrees Celsius inside the guts of a motor before the motor starts frying. Anyway, just remember, insulation level B, typical. So you have an insulation level for the magnet wire inside the stator, have a temperature rating that if you exceed that temperature rating because of short circuit and or ground fault or overload, this will trip.
Service rate, service factor.
Let's go back.
What's the definition?
Is that an or statement or an and statement?
Or.
One or if it's.
Thank you. Or. If you look at the code, it's an or. Very good point. Or. Either or.
So
Go ahead.
Yeah, can you kind of explain the service factor?
Absolutely.
It's not defined in there.
Absolutely. This is industry service factor 115. If I have a 100 horsepower horsepower, and if at service factor 1.25 or 115, I just picked a service factor, you can get to 125. This means this motor can be overloaded up to 1.25 times 100. That will give me 125 horsepower.
Right, but I mean,
What does that mean?
what does the word service factor mean for this? Or what's the
The logic behind it is you can abuse the motor more. You overload it more. It can handle more overload. It can handle, not forever though. I can't pull 125 horsepower forever. But I bet you if my machine is overloaded, say I'm running it 24 hours, right? And within that 24 hours, I can get an overload I need 100 horsepower. Most of the time 100 horsepower. But at certain time, I need to pull 125 horsepower out of it I'm going to say, dare to say 20 minutes. There's 20 minutes when things jams up, rush hour, and we're overloading it. 125 1-point service factor will be able to handle it. But 100 horsepower with one service factor 1, will trip. It will trip on you.
So you probably see a lot of, especially cooking appliances and stuff. Maybe have a high.
It's more for the machine. A lot of machines have at least 1.15 service factor. They allow you to overload it. Rush hour on the equipment. Too much pressure for a short amount of time though. So a lot of them, and if you look, it allows you to overload besides your overload higher, meaning you can overload the motor and the wires are not going to start burning. Make sense, Nick? No?
Yeah.
So that's my overload. Moving on. One little thing, guys, this is really interesting, especially if you're a project manager. Decrease and increase in the voltage. Decrease and increase in the voltage, guys. The utility is supposed to give you plus or minus 5% in the voltage. Sometimes they go as high, plus or minus 10%. So they have to maintain plus or minus voltage difference of 5% on the phases. Otherwise, your equipment start getting nuts. Take this as an example. If you go voltage variation, 10% extra voltage, your over voltage condition, the full load decreased by 7%. That's good news. Full load went down. Starting current increase. Oops. Now my starting current increase and the temperature rise. The temperature is going to decrease in your system, and full load speed will increase. Look what happened if you have a 10% reduction in your voltage. The current increased 11%. Now your motor is running at a higher current. The same thing, decrease in the start current. But look at the temperature. There's temperature increase and decrease in the full load speed. So we go over this in details, guys, with the electrician. For you have to understand. You walk into a building and the motors are hot, more hot than normal. Pay attention to the voltage that's coming to you from the utility. It has to be within 5%, plus or minus. Otherwise, your equipment will act weirdos. Percentage voltage variance to this is what the manufacturers allow you. There's a lot of, if you have 5% in the voltage difference, you're supposed to derate your motor by 75%. You know how they solve the problem? A lot of manufacturers. If you guys go to the code, that will help you a lot. If you have 100 horsepower at 460 volt. Anybody ever wonder why do they rate them at 460? Thank you. Now if you reduce it 5%, you're still okay. You can go, so the system's supposed to give you 480. So what's this one, Chris? 460 divided by 480. What's the percentage reduction? You have a calculator handy? Get it? 460 divided by 480. So look at this. That will give you 96%. I can reduce my voltage up to 96% of the nominal voltage, and my motor is still up and running. Did they come up with something similar? 96? Yeah. 96%. So they allow you to dip down. And still, the motor doesn't even feel it. You still can dip even higher because the motor is rated for 430. That's how they handle the voltage differences. They rate them at a lower voltage than the nominal voltage. This is just how fast how fast the overcomputation device can trip, guys. Dual element time delay fuse, non-time delay fuse, ordinary non-time delay fuse. Okay, so you can see that dual time delay fuse, dual time. This is what I want to. So time delay, it trips at 250 seconds if you have a time delay. If you don't have a time delay, Chris, it trips at what? 5 seconds. I promise you we're going to get into this one when you do the coordination. Remember that curve that I drew? That's how it's going to make the slope of that curve. That's why when we size this guy, we multiply by 300%. When we size this one, we multiply by 170% from the code. From 430.250 table. Why do you think we want to oversize this one? It's so fast. It doesn't allow the motor to start. Why do you think we undersize this one a little bit? It's slow. It allows the motor to start. Anyway, just keep this in mind, guys. But the higher the amp, the faster all of them go. The higher the amp, the faster. See, the amp goes higher here. The speed goes. The length goes smaller and smaller. The higher the amps, the faster it's going to trap. Short circuit. This is a couple of service factor rating for dual element fuses, guys. You can use them as a guide. Dual element time delay fuses, we have them in the book. This is the multiplier. This is your article 430.52 table. You guys are very familiar with this. The code allows you to go, if this doesn't work, please pay attention to that one. Here's your normal size. That's what you're going to size for. If you size based on 300%, but the motor keeps tripping, the code allows you to go higher even. But after you have proven that it doesn't work. So as designers, Nick, how are you going to prove it when you haven't designed it yet? So where's your default? Right here. We default right here. This is only under extreme conditions that you can, and these are all exceptions, you can go to higher than that. And I know we use this, guys. These were 175 that we use. Here's a 2.5 point for inverse type circuit breakers and so forth. We'll come to visit these when we size, guys, next quarter too. The last thing, almost on there, guys, you need a break. NEMA sizes. So Nick, you're going to hear about NEMA size for motors. The sizing based on NEMA. NEMA B is what you're going to remember, almost. NEMA B is good for all this stuff here. Normal start torque for fans, blowers, rotary pumps, unloaded compressors, conveyors, and all these are machines, very common, general purpose, blah, blah. All this is, you are almost defaulted to design B. What does that mean? When they design the guts of the motor, guys, they design it different. There are 4 designs. The higher the design, the more expensive. The D is a very expensive motor to buy a design D motor. They give you a lot of other applications. Look at this is the normal. The lock rotor current is very high, when starting torque is low. All of them are low, but this used in elevators, oil well pumps. There's application for each one of them. In a commercial building, you're always designed B without getting into too much details. And what does that mean? This means the guts of the machine. How do they design the rotor, and how do they design the stator of that machine?
So for lock rotor, it means kind of how fast it's gonna. Like let's just say it's got more torque than the B. The D has more torque than the B.
So look at the high, very high here, lock rotor. They used it for high inertia, things that you need to pull so heavy. Like you put all of you guys in elevator and I need to lift you. If you put a design B in it, that guy might say, okay, can somebody help me lift this? So design B, you might have 2 people helping design B start, but when it starts, it runs just to get you the lift. So they use it on heavy inertia. Does it make sense? Like elevators?
Yeah.
While B is a fan. What's on a fan? To run a fan. What's the inertia on it? Ah, Allah. You know what I mean? So conveyors, you fill a conveyor with the equipment and it stops. Now you're going to push a button and start. Imagine the inertia that you need to be able to pull these things together. So inertia or load. Starting, the ability to start, the starting torque, the ability to start things. So I want you guys to remember B for whatever reason, most common one. Okay, multi-mixers. The rest of them, guys, is calculation of what we have done. Any question? Any question? Nick? So that's what I know I didn't refer to the code because we know where these are in the code. We will be visiting in terms of calculation. We have done them, guys, we'll visit them again. I thought the concept, at least the concept of disconnect and overclock protection devices and so forth. Let's take 5 minutes break. So a couple of things, guys, if you don't know by now, please do. When we have any power system, you're going to have that utility coming out, utility coming in. The first thing you're going to have the service. Actually, this is covered by NEC in 230. You have an article. The NEC code book has a complete article that covers the conductor that's coming from the utility transformer into your building. You guys have sized multiple of them now. You sized 2 systems for Chad. And then when you take a feeder from the service, this is my service panel, you take a feeder from the service panel into another panel, that becomes a feeder, and this is covered by Article 215 in the NEC code book. And then you take a branch circuit, and that's covered by Article 210 in the NEC code book. So these are, guys, 3 important circuits covered by the NEC code book, and we use it in every type of building that we have, single phase or 3 phase. Does that make sense? Utility transformers, bringing the conductor single or 3 phase through a conduit and conductors to the service panel. From the service panel, you go to another panel that call it feeder. From the second panel, you go also to the last utilization equipment that's called the branch circuits. Any question, guys, about this layout? The reason why I like this picture is because it clearly defines if I'm looking for conductors for the service, which article in the NEC code book should I go to? 230, 215, and 210. Any questions about this? Any questions? So just a quick reminder, when we were doing branch circuits, your branch circuits most of the time they have a 20 amp. Most of the time, well, we start with it commercially, you're probably using 20 amp, 30 amp, 40 amp, 50 amp, up to 60 amps. Very common. Commercial lights and receptacles probably are sitting into the 20 amp and 30 amp for branch circuits. Feeders, bring it on. The feeder, my feeder here can be 100 amp feeder all the way to probably 3000 amp feeder. And the service here can be from 100 amp all the way to 4000 amp. That's what we do in Minnesota. They can allow you to go up to a 4000 amp service coming from the building. Make sense? Amp wise, voltage wise, guys, commercially most likely 208 here or 480 with 120 and with 277. Between these two, you covered 90% of your commercial industrial building between these 2 voltages, and the whole system goes through.
So if you get the 480, 277,
Yep.
you typically have to provide your own transfer.
Thank you. Yep, and that's what we're going to do in the next project, guys. We're going to take a 480, 277 and provide our own transformer. Because we, unlike in, first don't yell at me now, unlike in 80% of the world where they use 1 voltage, 380, 220, and then you don't have a transformer. If you design, guys, in 80% of the world, and it really is, you can have 1 voltage. And there's an advantage for that and disadvantage, of course. But for us in the US, we almost use 480 because it's high voltage, good voltage. And then the drawback of the 480 is you have to strip it down into 208, 120 to get the receptacles. Almost started here, Nick. I'm sorry. Okay, any question, guys, about these? Any question about, Nick, we just talked about the service coming to a service panel, feeder to a feeder panel, and all the way to utilization equipment. I want to bring to your attention, guys, when you are at the service panel, Chris, remember what we did here? Right at the service, we have something called grounding electrode conductor. We size it. We have something called main bonding jumper, and we size this. Can you guys see that, how we bond at the service? We don't bond here. We don't. Can you see the neutral here and the ground are not bonded, only bonded. And you also have this baby here is called service disconnect means. You have to have a main when you bring the power to your building. You have to have a main. I don't have to have a main here, guys. As a matter of fact, there is no main here. Can you see on the sub panel? You don't have to have a main. But at the service panel, you must have a main. You must bond the neutral to the ground, and you must provide a grounding electrode conductor. Remember that. I know we did this, and we will continue to do it. But this summarizes everything that we do for any building. Can I have thumbs up that, Chad, we got it? Cool? Okay. So that's what I thought. This is, again, this is not new, guys. We just a quick refresher here. This is also a quick refresher. If you guys remember how to use table 310.15b16, this is 310.15b16. Very, very important table. When you have 310.15b16, do you guys remember the rules that we said? I like it because it's a picture. Hopefully it will bring you home. Okay, let's look at the first rule. Rule number 1. If the terminals are 60, 60, and the cable is 60, for equipment, the equipment is 100 amp or less, or with conductor number 14 to number 1, you defaulted to, can you guys see what? The 60-degree column. See the default that I told you about? This is coming 310.14, 310.14, I believe. 310.14. Do we have it here? 310.14. Yep, the NEC code book 310.14. 310.14C1. This is all coming from 110.14. That's what I thought. 110.14C. 110.14C. Okay, so let's go quick with that baby. 110.14C terminals. C1, as a matter of fact, C and 1. Okay, so this is, we talked about this one. The second one, guys, if the terminal is 60, 60, and 75 or 90, conductors with higher temperature rating are permitted, but we still have to size based on 60, because we size based on the weakest length. Look at the cable here, is 75 and 90, but the terminals are 60. So when I go, which column am I going to go to under it? 310.16. Still 60 because the weakest link. So this is number 2. Number 3, if the equipment terminals are permitted, so we have a 75. If the terminal is rated for 75 in both sides, and the conductor is rated for 75 or higher, then I can go to 75-degree column, right? In this case, this is 60-degree column. This is 60-degree column. Okay, and for motors, number 4, for motors, guys, if the lugs, look at the lugs of the motor are rated for 75, the conductor are 75 or higher. So for these design of motors, I can go to 75-degree, no question asked. Any question, guys, about how to, so the only time I'm going to go to 60-degree is under these circumstances. That's my 60-degree, right? That's my 60-degree. I'm going to go to 60-degree. Or if the terminals, these two circumstances is 60-degree, everything else is going to be 75. Let me ask you this question, though. Suppose that this is 75, this is 75, and Nick decided to use a 60-degree rated cable here. Look at this. I decided single-handedly to use a TW, 60-degree rated cable between lugs that rated 75. Can I continue to use 75? No, they call it the weakest link. The cable have to be 75, and the two lugs on both sides have to be 75 for you to use 75. If you don't understand, if you don't know the terminals when we start, here's your default. Your default is number 1, right? Your default is number 1, 100 or less, or these conductors are 60-degree. Anything higher than 100 or more than number 1 is 75. Make sense? That's what we've been using, 75-degree column. Any question, guys, about this? Yes, Chris, you had something.
Oh, it just seems to cover an awful lot of wire. You need, 14 through one.
Yep.
cable for-
Yep. And if you guys look at this, if you look at this particular one, this is, I call it branch circuit. This is really the 100 or less, 14 through 1. This will constitute 90% of your branch circuits, right? Receptacles and lights and smaller equipment. Can you think about a lot of wires? Yeah. You go higher than number 1, you get into the feeders. This most likely when you get higher than number 1, this is here in this area. We're talking about feeders. The only exception is motors. Motors are the only exception. This is branch circuit, but exception for motors though. B, C, and D. Design. Remember, Nick, we talked about the design a few minutes ago. Design C. A is not here though. B, C, and D. The most common design we talk about all the time is what? Design B. So all your air handling units, all your chillers, everything is going to be design B.
We always
So
say,
motors are an exception of rule 1.
Yes. Absolutely. Yes. But it's still though, this come by design 75, this have to be 75, but the cable have to be 75 to apply the exception. Yes, Nick?
no, I was just gonna say, because motors, we normally.
75. Yeah. Based on this exception. And all this information is summarized, guys, in 110.14C1. And the table that we're looking at is 310.15B16 and other tables, but the most common one is 310.15B16. Any question about this? Can I get you to understand this 60, 60, 60, we're talking about branch circuits here, excluding the motors. Excluding the motors. So if we, so that's basically a thought. The second one, here's the rule. The second rule, this is also, please remember that one. This is also coming if the amps are over 100 or the conductors are over or larger than number 1. So larger than number 1, that will get you in a 1/0 all the way to 2000 kcm. From 1/0 right 2000 kcm. Is that the highest that we can get in the table? Yeah, 2000 kcm, you're going to go to 75. Granted, the cable has to be 75. If I put 60 cable, which will be full, to put a 60-degree rated cable here, then you go, it shifted you all the way to 60, the weakest link. But by design, by default, this one and this one at this is the default. If I spelled it right, this is the default. And what they're telling us, guys, you can have a conductors with higher temperature. Most of the time we use T, H, H, M. This is rated for 90 degree, right? But we use it here, but we can't size based on 90 degree. What do we use 90 degree for? Can somebody remind me? Thank you. Only for derating. So 90 degree logs, 90 degree Celsius is derating. Now, I want to, for those of you who are going to be designers one time, medium voltage, take this. If you have a medium voltage piece of equipment, between two pieces of equipment, now the logs, they rate them here at 90 degree. Take this, 90 degrees Celsius, 90 degrees Celsius. And if I am to use a cable between them, a cable that's that cable is 90 degree cable, and this is 13.8K, and this is a 13.8K kilovolt. A medium, this is medium voltage or so-called over 600 volt system. Over 600 volt system. Look at this. The code allows you to size based on 90 degree from a completely different cable. And I know we did a transformer based on this. So remember, this is for medium voltage. Now, you guys, all of you are going to be 99% of the time, you're going to be in this application. In a commercial industrial building, 99% of the time, you're going to be in this application, using feeders for 75 rating, only for receptacles and branch circuits that we use 60 degree. Okay, so we got that one. Harmonics. That will bring us, this is really probably one of the nicest things, picture that I can find about harmonics. Harmonics, guys, or nonlinear loads, they do not digest electricity the way everything else digests it. For example, I want to take you back to Mr. Ryman. You guys remember the linear relationship between current and voltage? For example, let me just take a tiny little example here and draw a very little example here and draw a relationship between the voltage. This is my current, and this is my voltage, and this is R, right? This is Ohm's law. R equal V over I. You guys remember that? If you take a resistor and you draw a curve and you take what different voltages, you guys did it in the lab. You take voltages, different voltages, and you measure the current. Voltage, that much current, so much current. You're going to end up with a line that represents the resistor. That's we call it linear load. Resistor is a linear load. If you take a motor, believe it or not, coil, and you do the same thing in coil to a limit, you're going to end up with the same R. If you take an electronic equipment that take DC, take AC, digest it to DC, and you draw the relationship, look what the relationship is going to look like. Something similar to this. If you do that, it's going to look something like this. So that's what we call it. If I take, this is non-linear, did they say it right? Load. And this is a linear load. And this one is, doesn't look right, linear load. Linear load and non-linear load. Any question, guys, about that one? Every time you take AC, convert it to DC, and dump it across electronic equipment, what have you done? You have created nonlinear load. What does that mean? When you draw the voltage and the current relationship, it's going to look like an ugly curve like this. It goes up and down and all over.
What's the final electronic equivalent?
Anytime you take an AC to a DC, diodes, transistors, anything that has a diode, anything that has a transistor, diode, you know what the diodes and the transistors, of course you know, diodes and transistors, thyristors, and a whole bunch of families that, don't take me there even, the NPN, what do they call them? Junctions, yeah. When you get into the NPN, anytime you have semiconductors, anytime you have a semiconductor equipment, which is all the electronic equipment, you get into a linear load. Okay, what we're interested right now, everybody knows the linear and nonlinear, right? I'm throwing all these one randomly here. Okay, now, this is just a relationship. Here's a linear, look at this, guys. This is a 60 hertz. This is a 60 hertz wave. Look how nice and beautiful this 60 hertz wave is. That's when you put a resistor, a heater, and plug it into 120, and if you go to an oscilloscope and look at the voltage, you'll look something very similar to this. Beautiful. This wave is the most important wave, natural wave, that all the electric equipment works beautifully on. They don't get overheat, they don't do anything. Now look what happened if I plug in that printer there that has an electronic equipment in it, or the ballast that right above your head for this picture. When you plug them in, because they're non-harmonic, when you analyze the signal, look what happened. Here's the fundamental. The fundamental for a 60 hertz system, fundamental is 60, okay? The third harmonic 3 times 60 is what? 180. This is 180. Fifth harmonic, 5 times 6 is what? 30. 300, thank you, 300 hertz. These are all hertz. 7 harmonic, 7 times 420, thank you. 420. And okay, so these are all these are different signals at different frequencies. That's no problem so far, except they're all mixed together and fit to the same equipment. So look at this, guys. Can you see the red one is the harmonic? The blue one is the third. The third harmonic means for every one signal of the fundamental, I'm going to have 3 signals embedded inside it. Can you give that count? Here's for the third one, third harmonic. Here's 1 signal. 1, 2, 3. 3 signals in 1 signal, right? Everybody knows 1 wave form, 1 signal. If it's a third harmonic, this means I'm going to go have 3 signals in 1 fundamental signal. Who cares? Yes, the frequencies are different. Look at the fifth. The fifth harmonic means in one 60 hertz signal, I want to have look at how many signals. When I have 5 signals on that color, the green 7 signals. We count the green signals, guys, from start 1, 2, is 1, 2, all the way 7 of them. Who cares? The question is, you're looking at me and say, who cares, Chad? When you add them up graphically, I don't know how many of you guys get into adding graph. Literally, take these points, right? Take a point here. Let's just take a point right here. And add this point to this point to this point to this point. You will get this point. When you add them graphically, the signal is going to look like the yellow signal. Who cares? Still to this point, who cares? This signal is ugly in terms of the effect on the electrical equipment. It heats conductors. It creates more heat. It creates more nuisance tripping because of that heat. On the neutral, it makes electronic equipment malfunction. It creates a whole lot of issues. That's where harmonic becomes a big deal. What equipment, motors, for example, what motors would like to see, they would like to see this one. Beautiful, smooth sinusoidal wave. You drop that one that looks, I don't know if you guys can see when you drop, they call it distorted signal. If you drop that signal now, which looks something like this, right? Look from this to this. Who cares? The electrical equipment don't like this. They malfunction. So that's where harmonic becomes a big deal. I want you to highlight the third, especially the third harmonic, guys. This third harmonic, without getting into proving it, when you have third harmonic, it adds up in the neutral of a 3-phase system. So if you have 10 amps, 10 amps, 10 amps, third harmonic, when you add them up in a 3-phase system, they don't cancel each other. They add up to 30. That's anti everything that we know about the 3-phase system. 3-phase system is supposed to have the balanced 3-phase system. If you have 10, 10, 10, what do you think that the neutral is going to have? 0. That's why we love the 3-phase system. Third harmonic is the opposite of that. You have 10, 10, 10, 10. On the neutral, what do you get? 30. Who cares? The question is always who cares? Well, you're going to burn neutral.
So don't derate.
That's it. Then we get into not derating the neutral because of that. Or having a larger neutral. Remember how we said to solve the problem harmonic in the neutral, guys? We either pull a bigger conductor, the phases will be 10, 10, 10, number 12, 12, 12, and the neutral will be number 10. Or we can reduce the amps. So if number 12 can carry 20 amps, if we can make it loaded 12 amps, by reducing the amps load, but that will reduce, of course, the current in the neutral. So no matter how you increase the current in the neutral, you're still what? You're still not getting not burning your neutral. Or better off, you pull a neutral with every phase. A neutral with every phase.
Size that neutral though?
No. If you pull a neutral with every phase, no matter what you do, you're not going to carry more. The neutral, if it's neutral with every phase, the neutral will never carry higher than what the phases carry. So, because neutral with every phase, it's just one phase, one neutral. Any question, guys, about the harmonic? So hopefully that will bring it home to some of you. Take this. In a heavily harmonic, if I have data center here, guys, I'm feeding right here data equipment. I'm feeding data equipment. This is very common if you have a data center. What's a data center? Imagine a room like this full of racks and racks of computers. And these are doing the transaction for Home Depot or any transaction or collecting security information or whatever. There's tons and tons of them. Google, every time you Google have a data center. They store the junk that Chad Kearney puts on YouTube. Who's going to store it? It's stored somewhere, not in my basement, stored somewhere for YouTube. I'm sure they have a huge data center somewhere. Okay, all this, when you add it, if you have 100 amp, 100 amp, 100 amp, it's supposed to add up to 0 on the neutral, right? Because of the third harmonic, they add up in 200 amp. Now if you size this one for 100 amp, suppose that these the conductors were, let's just use the rule, that would be number 1, right? Chris, at 100 amp, I want to size that conductor. That will be at 100 amp, that will be number 1. Suppose I size this one number 1, and I size this number 1. Now what's going to happen when you put a 200 amp in your number 1 conductor? You burn that baby. In a data center, guys, they go and they size the neutral double the phases. So for 200 amp double, I need, now you go into the 75 because it's higher, you need 3 aught. So the neutral here will be 3 aught. We have double neutral conductor size. Why? Because the harmonics, they add each other's, the third harmonic especially adds each other's on the neutral.
Are you looking on 75 or 60?
I was looking at, because I went 200 higher than 100, so I went to 75. Yeah.
Oh. Use these massive iron core that are called ultra-isolated transformers. What's the effect?
K-rated transformers.
Resistant to current change by the nature of the beast.
Absolutely. If you have a heavy, if you guys have a, we'll talk about this one, if you have a heavy rated harmonic equipment, what the utility give you, they give you a K-rated transformer. K-rated transformers, they are made in a robust way. Here's a transformer, they call it K-rated transformer. K-rated, and there's, I can't remember the values. They have different values, different K-rated transformers. So if you have a heavy harmonic load, you specify a K-rated transformer. Now what the heck is a K-rated transformer? K-rated transformer is designed by design. The guts of the transformer, the insulation between the windings is fast, bigger insulation, better wire that can handle all the stress and all the heat that's coming out of harmonics. Okay, so this is, guys, another, if you have a common 3-phase wire connected loads with ballast, you have 16, 16, 16, and you're going to end up with a 16 on that neutral. But you could end up, because of harmonic, if this is like ballast harmonic load, you could easily end up with more than 16 amps on that circuit. What was I? So we talked about this one. That resulted from nonlinear loads. So most of the time, guys, if you look at the 16 and 16 and 16 here, this should be 0, right? But it's not, because of the harmonics. They add each other's up at the neutral. Third harmonics add each other's up. Okay, we'll continue to, so how do you solve the problem? The question, how do you solve the problem? Polar neutral with every circuit. That will solve a problem, right? That's the most common practice. If you use a neutral, guys, common neutral, this is also another practice. This will be number 12. Let's make the neutral number 10. Right? I can pull a number 10 neutral, common. Not commonly used, because now we have to terminate number 10 and the receptacles that might not be rated for number 10. Most likely rated, but the first solution is the best solution. A Boland neutral with every phase. Okay, any question, guys, about the harmonic? I promise you we'll come and visit the harmonic a little bit later as we go through.
Number 10, what's the pigtail number 10 at the junction? And the box holding the receptacles?
Very good point. If you pull number 10, would you do they have an overcome protection device ahead of them? No. I can pick, if it doesn't have an overcome protection device, because the neutral doesn't land on a fuse, the neutral. And I can tab it with a conductor that equal to the load, which is probably, I would tab it from number 10. But if it's not landing on an overcome protection device, you can argue that you don't have to do that. Okay, so let me take you guys quick here. Oops, my conductor here. All right, so moving a little bit into the voltage drop, guys. The code for both feeders and branch circuits, the code say you can have that practices 3% voltage drop here, 2% voltage drop here, or no more, for no total than 5%. These are NEC recommendation for no more than 5%. So you cannot have the practice. The practice, guys, is when you have voltage drop, is you have to maintain the practice 3, 2, or 2, 3. The industry practice is you allow 3%, no more than 3% on the feeders because they're long, and the branch circuit is 2. What does a voltage drop means? Meaning if I started with a voltage right here of 480, I'm allowed right at this load here to lose 5% to 480. So let's take 5% to 480, 0.95 times 480. I'm allowed to bring this one to 456 volt. This is 5% to 480, right? 456 volt, right? Am I doing it right? So I can, if I started with 480, the load can see 456 and still functioning properly. Still function properly. Now what happens if you keep reducing the voltage? It will continue to work, but it will die prematurely on you. It will not function properly, meaning it might not give you the same amount of work that you do. And at a certain level, if you keep reducing until you drop this one to 380 volt, smoke starts coming out of it. Oh, well, there will be overcapacity device drops, of course. If it's a machine, you will have an overload that drops. But at one point, if there's no protection and you drop it to 380, you will burn your equipment. Because to compensate for the low voltage, what do you think the equipment is going to do to compensate for low voltage? They start sucking more current. Sucking more current, they're not rated for the current. What's going to happen to them if they suck more current than what they're rated for? Heat starts building up. Heat creates what? Fire. So that's a few things, guys, about the voltage drop. And we will do voltage drop, as I said, calculation. This is just a quick review. Okay, paralleling. When we parallel, guys, this is 3 runs. 3 runs, parallel 3 runs. When we parallel conductors, you have to, let me just write the rule where we got this information here. I want you to, because this will be very important when we go to the industrial project. This is coming 310.10H. This is from 310.10H. These are all rules coming from 310.10H. When you parallel conductor, they have to be the same length. They have the conductors to be the same material, copper or aluminum, the same size, same insulation, the same terminated in the same manner, with the same logs, same type of logs, and if you are separated, okay, the raceway or the cable must be. If you have a raceway or a cable, it must be the same type of raceway and the same type of cable. And I'm going to add, you cannot parallel, I'm going to add one more, so this will be 6 here, the raceway 7, and probably you guys know it, you cannot parallel this than 1 knot. You cannot parallel this than 1 knot, even if you want to. These are the rules for paralleling. Same insulation, same length, same material, same size, same termination. Here's the termination, means I can have a different lugs on the side, and same raceway, and I can't parallel this than 1 knot. Questions? So please remember that one, guys. Why would we parallel? The recommendation is, here's the recommendation when we parallel. If you have 400 amp, that can lead you into 500 kcm conductor. If you have larger than 400 amp, that need more than 500 kcm, parallel. Smart to parallel. 500 kcm conductor, guys, because of the rule in the code, allows you to be tied to a 400 amp. So if I have a 400 amp panel, 500 kcm, good enough, because of the rule. If you go higher than 400 amp, or the load need more than 500 kcm, parallel. What's the minimum conductor that I can parallel? 1 knot. Why do we parallel? Because it's a nightmare not to. Pulling a 2000 kcm conductor in a conduit, I don't know if you find a conduit to house 4 of them, or 3 of them with plus derated neutral. Any question, guys, about paralleling? The paralleling happened to every phase. Here's where you guys have to understand. Here's phase A, phase B, phase C, and a neutral. And this is phase A. Oops, why did they flip it? Phase B, look at that. This is phase B here. This must be the red. This oops, the black is what? The black is phase A. Okay, you just flip it. Phase A, phase B, and phase C, and the neutral. So if I ask you a lodipo, is phase A and phase B conductors are phase A and phase B conductors are parallel? Are they? Phase A and phase B conductors, are they parallel? No, only phase A conductors, 3 of them, and 3 phase C and 3 phase B, and the neutral. We don't parallel phase A with phase B, guys. That's short circuit. you parallel. What do you know? You know what parallel is? You grab the end of the cable, tie it together, then one end, and the other end you tie it together. Can you do that to phase A and phase B? You know what you get if you do that? Short circuit. Okay, that's a lot of confusion for a lot of people when they. Any question, guys, about this? So because of this, I'm going to throw this one just to confuse you a little bit. Take this. Can I make this conductor phase A copper and phase B aluminum and phase C, I don't know, let's say this is also copper. Can I do that?
Rule 3. Rule 2.
Okay, what does it say? Rule 2, be the same conductor material. Are the parallel conductor in A the same material? Yep. Are the B the same material? Yep. Are C the same material? Yep. But the phases don't have to be the same material. The conductor of the same phase have to be the same material. I don't like to even talk about this one because it's a weirdo way of doing it. But yes, you can have phase A all aluminum and phase B and C copper. The only thing you need to pay attention is that the lugs have to be rated for aluminum at the end, because phase A conductor and phase B conductor are not parallel.
So it should
I wouldn't do that.
Phase conductors must be.
Only the phase conductors must be parallel.
No, must be the same material.
Yeah, the same material. Yes.
Because both-
Okay, the same material. The same phase or the same neutral. Okay, any questions about this? Hopefully that picture brought the parallel home to you. When do you parallel? And when do you use parallel and so forth? Rounding up, conductor. Okay, typical. Okay. I just want to highlight this one for rounding up, guys. You can round up to 800 amp. And I will use this example and stop right here. I always use this example. This is phase A only. I'm paralleling conductor and I'm tying it to an equipment. Okay? So these are conductors. I'm using 500 kcm here and 500 kcm here. Okay? So if you take 500 kcm R kcm, if you take 500 kcm, if you take it to 310.15 B16, it'll give you 380 amps under which column? 75-degree column. Okay. And this is, by the way, 800 amp, and this is an 800 amp load. Let's just 800 amp. No, we don't want to do 800 amp. Let's just make the load 730 amp. The load is 730 amp. The overcapacity is 800. Okay. So if you guys take 380 and multiply it by 2, because I have 2 runs, that will give you 760 amps. 760 amps. If you take this one to 240.6, if you take this one to 240.6, what's the next standard? 800. These are the exception in the code. It says if the next standard after you pull the conductor's amps is not a standard. 760 is not a standard, so I need to put a circuit breaker. I can put 700, or I can go to 800. They allow you to go to 800, only up to 800. Now, if I have 1,000, I have to match the 1,000 amps. I have to match the 1,000 amps. So that's why you see a lot of panels, guys, 800 amp panel tied with two runs of 500. Even though if you add the 760, it had nothing. It's not even, well, it's not that close to 800 amp, and that's okay, legit. That's because of that rule. The rule of coming from Article 430 for 240. Any question, guys, about this rule? I don't like to use it being an engineer, but a lot of contractors use it because save you money. Okay, wire sizes. Okay, the last thing I want to talk about, guys, there's a couple of tables that you're going to use to size wires here. But for sizing wires based on voltage drop, I use a table in DWAL. So do me a favor, please. And that's the last thing I want to talk about. I want you to go to voltage drop calculation. Okay, let's go here. I want you guys, please, to go to page 1-22 in DWAL. 1-22 in DWAL, please. 1-22. If you guys go to 1-22, it'll give you the formulas that you need to do to find voltage drop equal 1.73 times rel RIL over 1,000, or you can use scale 1.73 times KIL over 1,000. These are the rules that we use, guys, to calculate the voltage drop for three-phase system, and we are dealing with three-phase system. And this is in page 1-23, 1-23. 1-23. Okay, so you can use a calculator. In a three-phase system, guys, these rules are great for DC and up to 4 aught. In an AC system, there are two types of resistance. There's resistance coming from the R and resistance coming from the XL and XC, right? Or so the Z component. Because of this, if you do me a favor and go to pay, and I'll go into this calculation, we'll do more calculation on these guys next quarter, but this, and we did last quarter. This is just FYI. If you guys go to page 1-23, this is commonly used practice. Go to 1-23, please. If you guys, the Smarter Than Chat did this calculation for you, okay? So if you look at the top, it says wire length versus size, maximum voltage drop. So maximum wire at 240 single phase, 2% maximum voltage drop. These are we use this as a guide already calculated for you for, can you guys see that? For voltage drop at page 1-24. Take this. If you guys have, I'm going to start with the number 20 amps. Can you guys go all the way to a 20 amps in the last column on the right side? The last column from the left or the first from the right on page 1-23. 20 amps. How far? And 20 amps on number 12 on page 1-24. Yep. And if you go to the middle of that table, and if you look at 20 amps on the right hand side, and number 12, how far can I pull a load that's 20 amps if I'm wiring it with number 12? Can you guys see? 70 feet. 70 feet. So take this. If I have a 20 amp load and the conductor is number 12, I can push that conductor 70 feet at 2% voltage drop and at a voltage of 240. So we'll tell you how far you can put your loads away based on a voltage drop with 2%. Why 2%? Branch circuits always 2%. 3% for feeders. Okay? I'm going to go to one very simple for you guys in page, the same page, 1-23. I'm going to take a good example, the same calculation here. I'm going to take this example. Take this. Here's a 20 amp. Oops. Very good. I think it's a very good example. Take a 20 amp circuit, and out of the 20 amp circuit, I'm going to pull a load, 20 amp circuit. I'm going to pull a load, and my load is, I'm going to make my load 15 amps. 15 amp load, okay? And the voltage is 120 volt, single phase, right? And I'm feeding 115 amps. And the voltage drop, it's a branch circuit. I need to maintain an engineered voltage drop of 2%. I can go to 3%, but bad news. You always, in the branch circuit, maintain it to 2%. So for 2% voltage drop, okay? How far can I put this load away from the panel? One more time. It's a 20 amp circuit breaker, and I have 120 single phase. I need to maintain 2% voltage drop. How far can I put this circuit, this conductor, this load away from the circuit based on this table? You can do the math, but based on this table, and the, oh yeah, I need a conductor. Thank you. I need a conductor, and let's just say the conductor is number 12. Okay, how far? So we have a 50, Dowling Thomas, 15 amp, number 12, single phase. What did you guys come up with? 47 feet. Anybody came up with something different? 47 feet. The bottom, we're looking at the voltage 120, the bottom side of the voltage. 47 feet. So they have to be, they can't be more than 47 feet away from each other. That's not a whole lot, is it? 47 feet.
I think it's 36, yeah.
You good?
No.
I'm sorry. I should have explained myself. When you size, when you size, guys, when you use this table, you go by the load. You always go by the load. You do not go by the overconduction device, because the load is the current that's going to go through the conductor. If my load is 15 amps, I go by the load. So my load is 15 amps, not 20. The load is 15, so I can 47. Any questions about this, how to use this table? We'll be using more of this next quarter. That's not a whole lot. Now, can I apply this rule to the lights in my room? No, mistake number one. Here's a branch circuit. And I add all the amps for the fixtures, and I came up with 16 amps. And oops, Chad, I violated 47. No. Anybody can tell me why can't apply this for these lights? For one simple reason. Are these lights all located, all of them, 47 feet away from the load? No. There is one fixture. If I come with branch circuit here, one fixture is probably, 10 feet. The other fixture way at the end is, say, 25, 30 feet. So how am I going to do that? This to be continued. How am I going to do that when the loads is scattered all over? This is only applies if a chunk of load thrown in one corner. Okay, everybody can know how to use this one. Very, very, very handy for branch circuit. And again, we will visit this one, guys, and as we move through. And the last thing before I promise you I'm going to stop here. The last thing I want to go is the page 125. Page 125 can get you the voltage drop for three-phase system. Page 125, guys. It says copper conductor 75, 600 volt single phase cable in a steel. This is for single phase cable in steel. Maximum circuit, so it's for single phase cable in a steel. That's what this applies for. Very, very strictly for that certain. And 60 hertz single phase 3-wire system with a balanced load. DC circuit single phase. Okay. So I want you guys to look at the voltage drop for single maximum circuit. Okay. So it applies actually for three-phase this table. Let's just take this. If you look at 4-aught, can you guys see from this table 4-aught? What does 4-aught gives you under 208? 208 volt. Okay, this is my condition. 208 volt, 3% voltage drop, 3% voltage drop, and the frequency is 60. What's what's the number? Can you guys find me the number between 4-aught from this table and 2A 3-phase? Anybody can see the number?
What's the
Four.
power factor?
What's the power factor? The power factor is going to be point. Yeah, that's a good point. Let's say a power factor of 0.85 power factor. What's the multiplier? 42100. Can you guys see that? Okay, so let's take this number. My number, Chad, from this table is 42100. Okay, so what does that mean? What does that mean, right? What does that mean? Well, it means if you take this, here's what you use this one. If I need the distance equal this multiplier divided by the current. Okay. D for the distance, M is for the multiplier. Here's M. And I promise we'll visit this one, guys. M is for the multiplier. And I is for the current. Take this. D is for the distance. How far I can push that one. Based on 3% voltage drop. This voltage drop 3%. This is a feeder. Okay, so let's take 42100. Okay, now, right, this is M. All right. I have a conductor of 4-aught. How much current you want to carry for 4-aught? Let's use the code. How much number 4-aught can give me? Number 4-aught from the table, guys, can give me 230. So 4-aught from the table can give me 230 amps. This is from 310.15 B16. Right? Okay, divide this by 230. And somebody, my friend, is going to do the. That's how far you can put a panel. How far you can put a panel from the source. So what we're doing here is really, here's my source, and this is my panel, sub panel. Here's my 200, in this case, 225 amp sub panel. This is 225 amp feeder. And what I'm trying to size here is the distance from here to here. This is my main panel. My main panel. There's other things coming out of it, of course. Okay, how far? What's the number? 183 feet. So if you have a 225 amp panel and you need to push it away at 2.8, and you need how far you can put this panel away from the source, the service, this table will give you how far you can put this panel from the service at the amp that you decided to use, which is, I decided to use the full amp of the conductor. Any question, guys? I promise you will visit this table more often as we go into the industrial. Okay, and I'm going to stop right there. And again, we promise they do them in different here. This is basically find the distance that from this table that you can push the load at that frequency, at that power factor. In 3-phase system, guys, becomes an AC system, the power factor become a big deal because the lower the power factor, the more current and the more the impedance would be. Any question for Chad? Okay, so that will wrap up this section. Thank you.